Today I will cover Chapter 16, Thermodynamics. I want to start by explaining what the difference is between spontaneous and non-spontaneous reactions. Spontaneous reactions occurs when something occurs without outside assistance, meaning that outside energy is not required. An example of this is a bike going downhill. You don't need to push a bike downhill, it just happens without outside assistance, and energy is not always required. Non-spontaneous reactions, on the other hand, occur only with assistance, and continuous input of energy is required. An example of this is pushing a bike uphill. You would need energy to push it uphill, and a continuous supply of energy would be required. Spontaneous reactions occur from ordered to disordered. A good way to remember this is like a room. Making a room dirty doesn't require energy. It becomes disordered without energy. But cleaning it does require energy. If a reaction is spontaneous in one direction, then it must be non-spontaneous in the other direction. For instance, with the bike example, pushing a bike downhill is spontaneous, so uphill would be non-spontaneous. Entropy is a measure of disorder or freedom of motion of the system. It is a state function, and its units are joules per Kelvin. The equation to describe entropy is S is equal to K ln of W. K is a constant. It is 1.38 times 10 to the negative 23 joules per Kelvin. Ln is just a natural log function, and W is the number of microstates. These are energetically equivalent ways to arrange the components. As the microstates increase, the S increases, or the entropy increases. And that's all you need to know about that concept. Predicting the signs of S, of the system. There are many ways that we can predict it, and that is by understanding that as entropy increases, the change in entropy is positive, and so the change must be greater than zero. That means it's spontaneous. But if the entropy is negative, then the change in entropy is negative, and it's non-spontaneous. An example of this is something going from solid to liquid to gas. In gas, particles are allowed to move more freely, and so they have more freedom of motion, and therefore entropy increases when going from liquid to gas or going from solid to liquid. In the other direction, entropy decreases, and so that's why it's non-spontaneous. The number of moles of gas in products, if the in products is higher than in reactants, then we know that a change in entropy is positive because the molecules or the reaction now has more freedom of motion. And this is true only for the system, not for the universe. And the number of moles of gas, if they're lower in the product and higher in the reactants, then we know that the entropy decreased and the change in entropy is negative. As temperature increases, the freedom of motion increases. So at higher temperatures, there is more thermal energy and more freedom of motion. And so entropy increases and change in entropy increases, meaning it's spontaneous. As temperature decreases, the freedom of motion decreases and entropy decreases, and the change in entropy is negative. Molecular complexity is as molecular complexity increases, such as the molecule gets larger or the molar mass gets larger, entropy increases. When a solid is dissolved in liquid, such as salt and water, it becomes part of the liquid, and so the freedom of motion increases. And therefore, the change in entropy is positive. However, when dissolving a gas in liquid, it goes from the state of gas to liquid, meaning the freedom of motion decreases, and so the change in entropy is negative. Second law of thermodynamics. The second law of thermodynamics is that entropy of the universe increases for a spontaneous process, and a chemical system proceeds in a direction that increases the entropy of the universe. Here's an equation to describe the entropy of the system, of the surroundings, and of the universe. We covered how to calculate the entropy of the surroundings, or how to understand it, in the steps above. Now, for the entropy of the universe is the sum of the entropy of the system plus the entropy of the surroundings. If a reaction is spontaneous, then the entropy is greater than zero. If it's non-spontaneous, then it's less than zero, and at equilibrium, the entropy of the universe is zero. Now, how to calculate the change in, let's say you know the change in systems from the processes described here. but you want to know the change in the entropy of the surroundings. An equation for that is here, where we use the enthalpy, meaning change in H of the system, divided by the temperature in kelvins. This is true because as there is more heat in the surroundings, the temperature increases, and as we know, as the temperature increases, entropy increases. So, heat goes into the surroundings when the reaction is exothermic, meaning that the change in H is negative. That's why that equation works. The third law of thermodynamics is that entropy of a perfect crystal at 0 degrees Kelvin is 0. Only one way to arrange the components in a perfect crystal, and that means the W, or the microstates, are just 1, and ln of 1 is 0, and that's why we know that the entropy is 0. The Gibbs free energy. Thermodynamics property includes all three factors that affect the spontaneity of a reaction: enthalpy, entropy, and temperature. It basically says G, the Gibbs free energy, is equal to H, the enthalpy, minus temperature times the entropy. And here are the units. I've stated them below. And it's important to remember that because the Gibbs free energy, the enthalpy, and the entropy are state functions, this would be a state function as well. If the reaction is spontaneous, then the Gibbs free energy is negative and the entropy of the universe is positive. Conversely, if the reaction is non-spontaneous, then the Gibbs free energy is positive and the entropy of the universe is negative. And at equilibrium, they are both 0. It's important to remember how the equation works and to know the different signs. So we have to understand that when the enthalpy is negative, and the entropy is positive, the reaction will always be spontaneous. And when the enthalpy is positive and the entropy is negative, the reaction will always be non-spontaneous. When the reaction is when both the enthalpy and the entropy are negative, it can be spontaneous or non-spontaneous depending on the temperature. And the same thing is true for when both the values are positive. So therefore, it is important to remember this, and you can usually plug these numbers into the equation or plug the signs into the equation and figure out what it would be. But it's good to have it in a chart when deciding. Standard entropy change. The entropy change of one molecule of a substance under the standard state. The standard state is anything at 25 degrees Celsius and at 1 atm. A good way to calculate the standard state of a reaction is by first adding up the enthalpy of the products and multiplying that by the coefficient of it, and then subtracting the sum of the standard state of the entropy times the coefficient of the reactants, and subtracting that from what you did for the products. Standard free charge in the Gibbs free reaction. The change for a chemical reaction under standard conditions as above. So to calculate the standard free change, we can do it in 3 ways. I will describe them below using a tabulated free energy formation. So this is again at 25 degrees Celsius, and when the change in the standard free energy change is 0 because it is a standard condition. And it is similar to the way that we did it for the entropy of the reaction. Basically, the change in the Gibbs free energy standard condition reaction is the sum of the standard Gibbs free energy of the product times its coefficient minus the sum of all of the Gibbs free energy of the reactants under standard condition times their coefficient. And you can also do this using a tabulated change in H and change in S of the reaction at any temperature. For instance, here we have a change in G with the reaction is equal to change in R reaction minus of the enthalpy, and we have discussed this in earlier lessons of chemistry, minus the temperature times the entropy, change in entropy of the reaction. We would use the equation here for this. And a similar equation for this. And basically we would calculate it, plug it in here, and find it. And this can happen at any temperature instead of the only 25 degrees that occurs there. The last way to do it is by modifying chemical equations to get the change in the standard free energy. We can do this because of the Hess's law, which says that chemical reactions can be expressed as a sum of a series of steps, meaning that you can add chemical reactions and in the end and get a final chemical reaction. When you reverse a chemical reaction, meaning you switch products and reactants, the sign of G, standard reaction, is also reversed, meaning that it becomes positive to negative or negative to positive. If a chemical equation is multiplied by a factor, then the value of G is also multiplied by the same factor. And when the chemical equations are added, the G values are also added. And that's how you do that. The free energy changes for non-standard conditions. To calculate this for non-standard conditions, you would have to know the change in G for standard conditions times R, which is a constant that we've discussed earlier, which is 8.314 times T, temperature in kelvins, ln of Q. Q is the reaction coefficient at equilibrium. It's basically when you have the equation for the reactants, not products times to the power of their coefficients, and then divided by the reactants to the power of their coefficient, that equation, and you write the Q value for that equation and plug it in here. Now, free energy diagrams. Free energy diagrams are useful because the slope of is the change in G, and the curve tells us which direction the reaction will proceed to equilibrium. So for instance, if there's more products or if there are more reactants, then here we see that when the reaction is going from reactants to products, that the change in G is negative and the reaction is spontaneous. When the reaction is going from products to reactants or shifting to the left, the change in G is positive, and so the reaction is non-spontaneous. We can see the same thing here, but relating G to K, or when it is at equilibrium, where the change in G is equal to 0 and Q is equal to K. So we get this new equation where minus RT ln of K is equal to the change in G at standard conditions. So when we see that K is greater than 1, meaning it's shifting to the right, or it's to the right, then we know that the G is spontaneous and it's negative. When K is greater than 1, the reaction is shifting to the left and it's non-spontaneous, and when K is equal to 1, the reaction is at equilibrium and shifts in neither direction. Relating G to Q and K. We know the reaction for this we discussed earlier was change in G at standard conditions per RT ln of Q, and for K it's minus RT ln of K. We can combine these equations to basically get something like this. And then we can understand when the reaction is spontaneous or non-spontaneous. If Q is less than K, then G is negative because the reaction will shift to the right. As we saw here, when the reaction shifts to the right, change in G is negative and the reaction is spontaneous. So we see the same thing here. When change in Q is greater than K, the G value is greater than 0, and it's non-spontaneous, and the reaction moves to the left. When Q is equal to K, the equation is at equilibrium, and it doesn't move in any direction. And that is it for chapter 16.